Good afternoon and welcome. This is John Morgan, Marketing Manager here at TMC. Thanks for joining our webinar on critical vibration control strategies. I just want to go over a few housekeeping rules and then I'll turn it over to Steve to begin the webinar. First of all, because we have a number of people, everybody's muted, but we do want to get questions from the attendees. So on the right, you can see a bunch of choices. If you click on the icon that says questions, please type your questions in, and I will read the questions to Steve at the end of the presentation so he can review them. Also, when you registered for the webinar, there was a place in the form to put in your AIA number so that you can get continuing education credits for the webinar. We did register this course at the continuing education site, and when this is all over, we will upload the list of attendees so you get your credit, and we will send you a certificate. If for any reason you forgot to enter your number or there was any other issue, you can see Steve's email right there on the cover page, steveryan@amatec.com. Please send him an email and we'll get it taken care of. So with that, I'm going to turn it over to Steve.
Okay, thanks, John. Thanks everybody for attending. So my name is Steve Ryan. I'm a Divisional Vice President here at TMC, and my background is physics, and I've been in vibration control for over 30 years. This presentation will be about 50 minutes, 50 minutes, and then we'll have a few minutes for questions. So what we're going to talk about here is the planning for building floor vibration in new advanced research facilities. And what I'd like to accomplish today is to help architects and planners have a better understanding for building floor vibration and what can be done to mitigate it, and how to use this information in the planning of buildings to avoid problems once the building is populated with tools. So the way the talk is going to be organized is, first I'm going to talk about the increasing demand for quiet sites in buildings with advanced tool sets, ultra sensitive tool sets. Second, we'll touch on the traditional approach to controlling vibration for these tools and why this traditional approach has become increasingly obsolete. Touch on what has replaced it and why. Fourth, we'll talk about potential problems you can run into and how to avoid them. And fifth, we'll talk about, related to all this, a novel idea that we have with an analogous precedent, and more on that later. And finally, we'll end with 3 case studies. So increasingly, these new advanced research facilities are being sited in urban environments, more generally environments that are hostile from a floor vibration perspective. So floor vibration really comes from 2 directions, either from inside the building or from outside, and they're the usual suspects. So externally, you have things like construction, road traffic, trucks, cars, and so forth, subways, light rails, trains. Also wind and acoustic. So, wind driving on a building will excite resonant structures of the building and increase the floor vibration. Acoustic, you have acoustic noise that impinges on the walls of the building and couples into structure-borne vibration, which drives floor noise and increases floor noise. And even seismic. And we talk about seismic, it's not so much, earthquakes or even the minor tremors and aftershocks, because those are relatively infrequent. But more things like other seismic events. For instance, there's something called the microseismic peak, and that is basically it's the cumulative effect of all the waves and all the oceans of the world crashing on the beaches. The net effect is this little bump at 0.2 of a hertz, which can be seen pretty much anywhere in the world if you've got sensitive enough seismometers. So that's the external stuff. The internal stuff, again, it's pretty intuitive, right? It's people walking, elevators, both freight and both service and the usual elevators, equipment, machinery. So you have things down in the basement of the building, air compressors, pumps, other facilities related equipment that generates vibration, and of course HVAC, because things moving through the ducts are connected to the building, and that it creates structure-borne vibration, which gets back to the floors. So the types of instruments that we're talking about, it's pretty broad. We're really talking about ultra precision instruments with extraordinarily high resolution, extraordinarily high magnification, extremely tight tolerances and so forth. So one of the hottest areas we're seeing right now is the construction of advanced microscopy centers, typically in universities. So microscopies spans a number of different microscope techniques. There are optical microscopes using different techniques to get extremely high resolution, techniques like super resolution, confocal, single and multi-photon microscopes. We also see a lot of work with electron microscopes, scanning electron microscopes and transmission, but also things like atomic force microscopes, scanning probe, scanning tunneling microscopes, all getting down into that nanometer, sub-nanometer, angstrom, even sub-angstrom kind of resolution range. Nanotechnology facilities and the nanofabs, also electron microscopes and dual beam instruments, right? So ion beam, electron beam combined to do milling, electron beams for lithography. We also see a lot of activity in new photonics centers. A lot of work in virtual reality, very vibration sensitive, holography, interferometers, and even ultra high energy lasers up to petawatt lasers, so 10 to the 15 watt laser facilities are becoming increasingly popular around the world. And finally, semiconductor manufacturing sites. So semiconductor manufacturing tools are sensitive both on the lithography side, laying down the pattern on the wafers and on the masks, as well as the inspection. So inspection of the finished wafer, surface metrology analysis, failure analysis of defects in a lab, and so forth. And just to kind of put in scale what we're talking about for this, particularly on the semiconductor manufacturing side, a defect review, right? Trying to do a deep dive and analyze a defect in an integrated surface, in an integrated circuit on a a patterned 12-inch silicon wafer. The scale that we're talking about, the scale of that defect on the wafer, is the scale of in trying to find an ant in Manhattan from a satellite. So that's literally the kind of scale that we're talking about. Or another way to think about it is laying a sheet of drafting paper over an entire football field and having a draftsman lay on their stomach and draw lines with the finest drafting pencil, finest lines as close together as you possibly could. That'd be the kind of density we're talking about. So extremely high resolution and therefore extremely sensitive to a little bit of floor vibration. So there is, driving all this, there's this very broad, decades-long trend in discrete part manufacturing, the manufacturing of any part, whether it's normal scale or precision or ultra precision or beyond that. What happens is that as time goes on, the tolerances on these parts get tighter and tighter, and the corresponding resolution for imaging type equipment gets higher and higher. So a good example of this that people in the semiconductor industry are very familiar with is called Moore's Law. So Moore's Law goes back to the 1960s, stated by Gordon Moore, the co-founder of Intel. And he stated that every 2 years, the number of transistors you can pack on an integrated circuit doubles. And this just keeps marching along. It's driven by a combination of physics and engineering and economics and all sorts of things. But it continues to drive things. So things like an integrated circuit, tolerances just get driven at a very, very predictable rate, density doubling every 24 months. So a lot of people are familiar with that one, but we see it in even more extreme applications. For instance, there's an instrument, a technology called nuclear magnetic resonance spectroscopy, and that's basically the physics that does an MRI, right? An MRI, they don't like to use the word nuclear because people get scared off, but it's nuclear resonance and has nothing to do with radiation. NMR spectrometers are used basically to look at, if you have a torn ligament in your knee, you take an MRI and they use NMR to image your ligament. But it's also used in high resolution applications where you might have a very, very, very small amount of biological material. And it's looked at in a very high resolution way to create things like a 3D model of a molecule for drug discovery or pharmaceutical research. NMR spectrometers, similar to Moore's law in semiconductor manufacturing, NMR spectrometers, if you go back even 30 years, the most advanced ones in the world, these superconducting magnets, were just sitting on rubber pads on the floor. And since then, they've all migrated to have airbags supporting them, and then to more sophisticated self-leveling air isolation systems. And now the most advanced ones in noisy environments will have a combination of a very sophisticated self-leveling air isolation system stacked on top of a active feedback vibration cancellation system. So 2 stages of isolation. That's just another example, something that rubber pads were enough 30 years ago. Now their resolution is so much higher that they need to resort to really extreme vibration control methods to get the instrument to work to its performance specifications. And those are just a couple of examples, and we see it everywhere, really increasing. So there are a set of curves called the VC curves, or vibration criteria curves. And these were developed by a vibration consultant, Cullen Gordon Associates, a number of years ago. And the goal of this was really to just create a common language so that tool manufacturers, creating specifications, could communicate with, lab directors, architects, vibration consultants, solutions providers that design and manufacture vibration isolation systems. Again, just to provide a common language. And they have evolved to the point that typically ultra-sensitive instruments use one of these VC curves as their vibration criteria for the instrument. So these are very helpful and very widely known. And this also in the VC curves, we see evidence of the increasing vibration sensitivity of tools over time, because as recently as 1991, the VCE was the lowest vibration criteria defined. And now it's not uncommon to see things like electron microscopes with specs down to below VCE, all the way down to VCG. So the curves basically are showing, you see the horizontal scale there is frequency from 1 hertz up to 100 hertz on a log scale. The vertical scale is velocity, right? So when you measure vibration, you can measure it or express it in terms of displacement, velocity, or acceleration. So they're defining these curves in terms of constant velocity over frequency, because that tends to correlate with the sensitivity of tools. Tools tend to correlate more with constant velocity over frequency rather than constant, say, acceleration. Just put these numbers in perspective, something like the VCE line, that's at approximately 3.1 microns per second of velocity. So what's the traditional approach for these things? The traditional approach has been to design quiet buildings and locate isolated concrete plinths underneath the vibration sensitive tools. So plinths are typically poured concrete blocks or some sort of a hybrid of concrete and steel. And we see them really falling into 3 different types. One is a concrete block on rubber pads, and you can see the top left photograph there, the rubber blocks at the bottom of a pit before the concrete block has been poured. So you're going to have a large concrete block on rubber pads. The second would be shown in the lower left-hand photograph. There's a capital T-shaped concrete plinth with a shelf supported by self-leveling air springs. And finally would be a concrete block that's just decoupled from the building. So rather than rubber pads or air isolators, it might be on sand or something else just to decouple it. But from our perspective, those are all the same thing. They're all mass spring dampers. You've got a mass on a damp spring, and even sand is going to behave like a spring, and that's what we see. So the advantages of this type of approach is that it's time proven. It's what people have done for a long time. It's simple, relies on the simple physics of F equals ma, right? The larger the mass, the more force it's going to take to accelerate to a given vibration level. So simple, reliable for a long time, but it's becoming increasingly obsolete for a few reasons. One is because tools are becoming more vibration sensitive and specifying ever quieter floors. It's harder for this fairly crude approach from a vibration control perspective. It's hard for it to keep up with the quieter and quieter levels that you need to get down to. Second is because it's passive, which I'll get into in a minute, what passive is all about, but because it's basically a mass spring damper, there's always a characteristic resonant frequency at which it amplifies. And that amplification actually makes the floor vibration problem worse over some frequency range. And in some cases makes things worse than no isolation at all. And finally, a really critical reason is that all the ultra-sensitive instruments have built in a vibration isolation system already, something fairly sophisticated, typically a low frequency air isolator to filter out high frequency vibration, but amplify at their resonant frequency. So if you've got say an electron microscope that has low frequency air isolators in it, if you place it on a plinth that's supported by low frequency air isolators, you can run into compatibility issues between the two sets of isolators being stacked on top of each other. So basically what we're seeing is, it's becoming increasingly difficult for the plinths to provide the required isolation, especially at the low frequencies, like below 10 hertz. So I'll talk a little bit about what passive vibration isolation is and what active vibration is. Have the treatment be fairly short, but basically a vibration isolation system, a passive isolation system, is a mass spring damper, and it's depicted in the upper two schematics there. You've got a mass on a damped spring. And when you have a mass on a damped spring, you're going to have a characteristic resonant frequency at which you have amplification and above which you start to isolate. So the lower graph is showing frequency on the horizontal scale, again in log scale, so at like half a hertz up to about 20 hertz. And vertically, in the vertical axis, you have transmissibility or the transfer function. So there's a 10 to the 0 there, so that's 1, that's unity. Anything above that 10 to the 0 is amplifying, anything below it is isolating. So when you have a mass spring damper, what's really critical is the frequency of the mass spring damper, based on the stiffness of the spring, and the amount of damping. So to get a high degree of isolation at high frequencies, the problem is that means light damping, and light damping means more amplification at the resonance. So the Q equals 100 curve, where you have almost 2 orders of magnitude amplification at 1 hertz there, that's the one that gives you the steepest roll off at 10 hertz, 100 X reduction at 10 hertz. So there's this inherent trade-off with a passive vibration isolation system. The more isolation at high frequencies, the more amplification at low frequencies. The less amplification at low, the less isolation at high. And it always comes with that compromise. Now, we're talking in simple terms here. We're just depicting this as a single degree of freedom problem, just showing this in the z-axis. But of course, vibration is 6 degrees of freedom. It's all 3 axes, X, Y, and Z, and it's pitch, roll, and yaw, the combination of those axes. So we're going to talk about the simple case of a 1 degree of freedom, but of course, this is a 6 degree of freedom problem. So going from a short treatment of passive vibration isolation, we'll go to active vibration isolation. So there are 2 types of that. One we would call parallel, the other we would call serial type. And that serial and parallel refers to whether the force actuator that's canceling vibration is in series or parallel with the spring supporting the payload. So in the case on the left, you have the passive mass spring damper, and we've added a sensor to the isolated payload, a vibration sensor, accelerometer or velocity sensor perhaps. And we take that signal and we condition it and run it through a controller and then a power amplifier. We run it back to a force actuator that provides an equal and opposite force. And there's one axis there. And of course, we need to do that with 6 sensors and 6 actuators to do 6 degrees of freedom. But basically, you've got a mass spring damper that's isolating. And what the active controls do is they allow you to eliminate the amplification at the resonant frequency. So you get the best of both worlds. You continue to isolate high frequency vibration as if you had very little damping, but yet you don't get the amplification at resonance because you're canceling that based on the feedback system. And that's very helpful, and it's the type of active system that you would typically see designed into the most sophisticated tools. Not so much used under the floor for reasons we'll talk about in future slides, in upcoming slides, but because it's the most effective advanced system to design into a tool. The second type is on the right, and that's a serial type, and there we it's a little more complicated. The mass spring damper is shown schematically on what we would call an inner mass, this little block. The sensor is on the inner mass, the vibration sensor. And we take the signal there, condition it, amplify it, right, run it through our controller, and then back to a force actuator. But this time the force actuator, rather than being like a linear motor or a voice coil in the parallel type, it has to be stiff and capable of supporting the payload. So it would be something like a piezoelectric ceramic piezoelectric stack that that can bear thousands of pounds of load. So if you imagine, the floor moving up and down there, the inner mass is going to move up and down, right? Because the force actuator is stiff, the inner mass moves up and down. We sense that, and we take that signal and we use it to expand and contract that piezo, right? So as the floor moves up, the piezo contracts, it moves down, it expands. So you keep the floor motion from getting to the inner mass, and then you get additional isolation from the spring damper. So the advantage of this type is that the spring ends up being very, very stiff, like a very stiff rubber pad. And what that means is the vibration isolation that's built into the instruments, typically a low frequency isolator, will now be on a very stiff isolator. So there's inherent compatibility. So in terms of trying to stack an isolation system on another one, the lower isolation system would need to be the serial type because it's much, much stiffer, and you don't have problems associated with crosstalk of a low frequency spring on a low frequency spring. So this shows a couple of different transmissibility curves for different plinth types. So in the top right, it's a little bit of a busy chart, but in the top right, you have a concrete plinth supported on, say, very stiff rubber pads, right? And that would be the blue curve. So the blue curve, again, horizontally is the frequency range from 1 hertz to 200 hertz. And vertically, in the vertical axis, anything above 0 is amplification, below that is isolation. So the blue curve is a plinth on rubber pads. And you can see there that at about 20 hertz, which we've chosen as a typical frequency, you get about an order of magnitude amplification. And it starts to isolate above 30 hertz. But you really, by those high frequencies, they're really not such a concern. So that's actually amplifying more than isolating in the critical frequency range, and probably going to make most problems worse. The red curve is a plinth on a self-leveling air spring isolator, showed in one of the previous slides, a much softer isolator. So there we're showing a resonant frequency of just under 2 hertz. You can see again, amplifying by an order of magnitude at 2 hertz, but by 3 hertz, you're actually getting some pretty good isolation and very good isolation at high frequencies for a plinth on self-leveling air springs. And finally, the yellow curve, or the gold curve, is the serial type active isolator, right? So you might compare a plinth on air isolators in the red curve to a serial type active system, which is the yellow curve. And the difference in performance is the gray shaded region. So you get all that additional vibration isolation at low frequencies. So you might say, well, that's true, but at higher frequencies, the plinth on the soft springs is better, right? The red curve is below the yellow curve above about 15 hertz or so, 10 hertz or so. And there are two reasons that that's not really important. One is that really at frequencies above 20 or 30 hertz, floor vibration coming up is really a non-factor, because at those higher frequencies, we're always seeing the environment controlled by acoustic coupling or self noise in the tool, or mechanical coupling. Vibration isolation above 30 hertz for these kinds of applications is not really relevant. And the second reason is that the tool is already going to have a low frequency air isolator built in. It already has something like that red curve for transfer function for the internal one. So it's amplifying at low frequencies. So it doesn't need any help at high frequencies. What it needs to do is counteract that amplification at low frequencies. So that's why it makes a lot more sense to gain the gray shaded region and than to give up the difference between the red curve and the gold curve at higher frequencies. So this is just a little bit of a visual to drive this point home about compatibility between isolators. So you've got A is the vibration isolation system that's built into the tool, and the image, the cartoon on the right, is basically the top of it is the tool's vibration isolation system, and the bottom is the plinth's vibration isolation system. So you can just kind of intuitively see that if you have two soft sets of springs, they're not going to behave very well. You're going to get if you have an order of magnitude amplification of the upper spring and an order of magnitude amplification at the lower spring, and they're at about the same frequency, say 2 hertz, now you've got 2 orders of magnitude amplification, which is a problem. The other problem, of course, you have is just stability issues. Stacking low frequency springs, just the basic physics starts causing you problems. So really the takeaway is that, with isolators, with vibration isolators, even a good vibration isolator can be counterproductive if it's not inherently compatible, if it's being stacked with another vibration isolation system and it's not compatible. So we've talked a lot about 2 hertz. What's so important about 2 hertz? Well, there are several things that contribute to that being kind of a critical number. The first is human walking. So these buildings are populated with people typically, and the time period of human walking is about half a second. So what you end up with is the cumulative effect of a group of people walking randomly is around 2 hertz, is driving the floor at around 2 hertz. The second thing that contributes to it is, as I mentioned before, typically the most advanced tools, electron microscopes, NMR spectrometers, wafer inspection machines, atomic force microscopes, these will all incorporate something like a 2 hertz air isolator typically. So you've got amplification by an order of magnitude at 2 hertz, and you have people walking that's driving the floor at that frequency where you're amplifying, so that's bad. Third is when we go out and measure floors in all sorts of buildings, it's not at all uncommon to see resonant behavior of the floor itself at 2 hertz. That's not good, but it's one more thing that's contributing. So you've got isolators amplifying, floors resonating, and people driving that frequency. So it's making a bigger and bigger problem. And finally, as you get below 2 hertz, it gets more and more difficult to isolate vibrations, or requires much more aggressive, complex, and expensive approaches when you start getting to very low frequencies. So 2 hertz comes up over and over again. So one of the things that becomes apparent is that it's very important to plan ahead for certain things that are going to happen in a building that's designed for supporting these kinds of tools. And one is this phenomenon that vibration levels on the floor will rise over time. So Colin Gordon Associates, again, vibration consultant, published a paper back in 2004, and they studied one of the buildings that they were working on, and they saw that in the first 17 months, the vibration levels on the floor rose by 15 dB. So you can see the curves there. The red curve was the as-built, right? When the ribbon was cut and the building was done. 14 months later, they went back in and again in 17 months and took more data, and you could see the vibration levels rising. Well, there's no reason that should be a surprise, because when the building was first opened, there's nobody in it. Tools still have not been installed. There's not a lot of human activity. There's not a lot of mechanical activity. And as time goes on and the building gets populated with people and things, the vibration levels are going to rise. So this is important because decisions can be made at the time the building is open, right? When the building is opened and things are just getting started, if floor vibration measurements are taken and it's determined that a particular spot in the building meets the vibration criteria of an instrument that's going there, that may be true when it's first installed, but you could easily have a situation where a year and a half later, that tool is not meeting its performance specs because the vibration levels exceed the vibration specs of the instrument by 15 dB or potentially even more. So this is an example that provides some insight. This isn't one of the case studies that are coming up, but this is just an example of a plinth installation and the problems associated with different types of vibration isolation systems. So this is a case of an immersion lithography stepper. It was installed at Semitech, the Semiconductor Consortium in Austin, Texas, and it was trying to lay down, as part of its installation and qualification, it was just trying to lay down a test pattern. It's a lithography tool, so it was trying to put down the pattern that you see at the bottom right. Just a lithography tool to lay that pattern down on a silicon wafer. And the plinth was a combination of concrete and steel, bridging the gap between the raised floor and the subfloor below it. And the performance was very poor, and they were not able to create the pattern. So they retrofit the plinth by putting rubber pads between the plinth and the subfloor. And you can see both of those down there on the chart in the bottom center. So the white line is the vibration levels across the frequency range of the initial plinth. And then when it was retrofit to add rubber pads, that's the green line. So this shows it very clearly what we were just talking about. At higher frequencies, because you have vibration isolation in there now, you eliminate all that high frequency noise above, say, 20 hertz. It's pretty much gone by above 30 hertz. But at 5 to 15 hertz, you can see a tremendous amount of amplification, right? It's a mass spring damper. Its resonant frequency is clearly 10 hertz in the vertical direction there, and it's amplifying the problem. So the problem actually became worse, and the test pattern ended up looking like the image in the top right, which was worse with the rubber pads than without the rubber pads. So literally going from no isolation to some vibration isolation made the problem much worse. And ultimately, the Semitech had to pull out the rubber pads and install, a very sophisticated serial type system, and then they were able to get what you see in the bottom right-hand photograph. That was the final result. The patterns that they were able to lay down were nice and clear and sharp. And in the image in the bottom center, that's the turquoise curve. That's the vibration isolated levels after the rubber pads were pulled out and the plinth was supported by a serial type active system. So what's going on? What's going on is that because tools are more and more sensitive and their specs are getting tighter and tighter, there's pressure for architects to design buildings to ever quieter specs. And this is becoming impractical and very costly to design quieter and quieter buildings. You reach a point of diminishing returns, and to some extent, it's not even possible because you cannot have a building. You can't have the vibration levels in the building lower than the vibration levels on the greenfield site that the building is constructed on. Right? Buildings are structures, and structures amplify noise. They don't isolate it. So at some point, you can't get past the vibration levels that are on the earth at the site you're locating the building. So there's kind of a dead end here. As you need to design quieter and quieter buildings, at some point it becomes impractical or even impossible. And to just kind of show in the top right there, we show a depiction showing a before and after. It's an electron microscope image where there's some floor vibration that exceeds the spec of the tool, and you see those kind of wavy edges to the sample. That's floor vibration artifact, and the higher frequency kind of hair-looking stuff is magnetic field distortion. Higher frequencies like 60 and 120 hertz. And in the bottom right, what you can see is that a floor, the red curve, that exceeds, say, the VCB level is able to be brought all the way down to below the VCE level, so a jump of 4 VC curves plus by going from just the floor to one of these serial type active systems, right? So the difference in terms of where you might design a building, say 1 VC curve, you can get down to 4 or even 5 VC lines below that with proper planning on a vibration mitigation plan. So the idea is, why freeze the whole house if all you want is a cold beer? And the analogous precedent is this. Floor vibration is an environmental contaminant, an environmental artifact, if you will, that prevents these ultra-sensitive tools from meeting their resolution, but so is cleanliness. And we saw in the semiconductor industry over the course of decades that as each new smaller node was reached, increasing cleanliness of the clean room was required so that you wouldn't have contamination of the IC. Smaller and smaller particles would be able to lead to a failure on an IC. So the cleanliness specs were getting so extreme, it became clear that it was unsustainable. And just the depiction there, just kind of a facetious depiction of an astronaut suit, it became clear that you wouldn't be able to even have people working in a semiconductor fab, even in an astronaut suit, because just moving your arms and legs generates particulate from the suit. So it was a real problem, and the fundamental change was to give up on trying to make the clean rooms cleaner and cleaner, and focus on having these finite little mini environments that SMIFs and FOUPs basically. Many environments that are roughly a 1 foot cube where an extremely high level of cleanliness could be maintained because they were so small. So the wafer stacks were placed in these FOUPs and moved around with robots in the fabs, and the wafers were not exposed to the air of the fab. They were only exposed to the air inside this little mini controlled environment. So rather than trying to make the clean room cleaner and cleaner, they focused on these little mini environments being extremely clean. And it's pretty clear that floor vibration is heading in that same direction. You can't make the buildings quieter and quieter. At some point, you're running down a dead end. At some point, you have to focus on being less aggressive with the building overall and focus on having a few dozen discrete locations in the building be ultra quiet. So we'll go into 3 case studies, and the case studies to some extent all touch on what's called the cryo-electron microscopy. A lot of these advanced research centers are using cryo-electron microscopes, and that's a Nobel Prize winning breakthrough. It came about in the around 2013, and it allows for extraordinarily high resolution images of biological materials. So normally in an electron microscope, there's a vacuum chamber and you're blasting something with a high energy electron beam. So it's fine to do that with a piece of silicon or some sort of a materials analysis or metals. But when you have a biological sample, you can't really put it in a vacuum chamber without changing or destroying it. And you can't hit it with a high energy electron beam without destroying it. So the breakthrough was sample preparation. So biological samples could be prepared and be compatible with going under these electron microscopes. And just to put it in perspective, that rendition there in purple, the left side of it is the highest level of resolution of of the Zika virus prior to 2013. And the right side of it depicts the level of resolution that was possible using these cryo-electron microscopy techniques. So if you're doing something like studying a virus like Zika or COVID, or doing drug discovery for cancer or anything really, being able to get a three-dimensional image down to the molecular scale where you can actually image individual atoms in a complex molecule, it's just extraordinarily important for researchers. You can see the difference between the left half of the image and the right half of the images. It's just simply night and day. So there's really red hot interest in cryo-electron microscopy, and these advanced microscopy facilities are showing up quite a bit. So the three case studies we'll talk about, one is a renovation of an existing building. One is a new construction where a design change had to be made right in the middle of the project. And the third was what we consider kind of best practices scenario, new best practices case, and that is new construction building where no changes needed to be made. So the first case is New York Structural Biology Center. So this is an urban environment in Upper Manhattan. It was renovation of an existing building. There was a 5-foot thick plinth in a room that had to house the instruments. And the plinth was basically wall to wall. It wasn't just a little section. It was 5-foot thick concrete, wall to wall, separated from the rest of the building. So the plinth wasn't really customized to the footprint of the tools that were going to be located there. And there were lingering concerns that city activity changing over time would impact the future tool performance. And there really wasn't any sort of an upgrade path or any sort of a plan they could come up with to lower the vibration levels if the plinth turned out to be not an adequately quiet environment. So the decision was made during the renovation, to dig a pit into the existing plinth. And I'll show that pit in the next slide. But basically what you've got here is a couple of instruments. On the left, you've got a dual beam tool that would be supported on a conventional isolation platform. But the image in the center is the cryo-electron microscope, the gray and white two-tone housing is around the cryo-EM. And you can see that what it requires is there's an inner vibration sensitive core of the tool that sits on a vibration isolated platform, and then the outer portion of the tool needs to be supported separately and not on the isolated platform so as not to degrade it, but supported on a rigid structure that goes down to the subfloor. So this is what it looked like. So here's the plinth that goes all the way out to the walls. It's 5 feet thick, and what they did is they went down about 2 feet deep into the pit, into the plinth, to create a after the fact pit. So quite disruptive, time consuming, delayed the project. It's messy, noisy, really just a mess. And but this is what they had to do to provide the insurance they thought they were going to need to, again, ensure that they'd have quite enough vibration levels to meet the needs of the tool going forward. So it was you can see the plinth has had the pit dug into it in the image on the right, and you see the two platforms, an outer ring platform rigidly supported to the base of the bottom of the plinth, and an inner isolated one supported on isolators supporting the core vibration sensitive part of the tool. And just backing up, so that was extremely successful, and they were able to achieve the high resolution with the instrument without vibration problems being observed. So the second case is MIT Nano in Cambridge. So MIT Nano was a project where right in the middle of the project they had to make some changes. So the initial plan was the exact tool set was unknown. The team wanted to delay the tool set decision as long as they possibly could in spite of a very strict timeline, because they wanted to have access to the most advanced tools, right? So delay the decision so you can get the most advanced tools that you want at the last possible moment. But the unknown tool set means unknown vibration criteria. So the team wanted each tool owner to be able to choose their own preferred vibration isolation method. So they designed the facility with plinths and pockets so that each tool owner could put whatever isolation under the plinths that they wanted. So that was the plan. And the problem that they ran into was that the building had much higher levels of vibration at a critical range, 3 to 4 hertz, than they had expected. And so the building failed to meet, by a fairly wide margin, the tool specifications, which were in some cases VCF and VCG. So the drawing on the left is a cross-section of the T-shaped plinth supported by air isolators, right? The ones that would be chosen later by the tool owners, depending on what they wanted. And the images on the right show what they ended up doing. So because the floor vibration levels were too high, they ended up having to go with a serial type active system. Couple of advantages, not just to get down to the lower vibration levels that they needed, but because the concrete plinths were not customized to the tool footprint, right? You had the inner vibration sensitive portion of the tool resting on the concrete plinth and the outer non-vibration sensitive portion of the tool that's noisy sitting on the same plinth, putting vibration right back into the surface that you're trying to isolate. So one of the options that they had was to put active isolators under the plinth, but that was going to be very expensive because of the high mass of the plinth. Very high masses are expensive to isolate with active systems. So instead, they replaced the plinth in the design stage, right in the middle of the project. They changed the design to go to these active point of use platforms rather than plinths. So the curves on the left, you could see the red curve is the floor, the blue curve is the point of use active vibration isolation system. The one at the bottom shows that 3 to 4 hertz resonance in the floor in the red, and how much it can be reduced by the serial type active system. The green curve is the spec, so they're below the spec, but that spec was just a snapshot in time. They also did some longer surveys, 24-hour surveys and peak hold surveys, where the floor vibration data was substantially over the spec. So basically what it does is demonstrate the need to be conservative. You can see that the vibration starts to be mitigated down below 1 hertz, and it's about an order of magnitude at 30 dB. At 30 is an order of magnitude or more, 30 dB at higher frequencies. And finally, the last case is Oregon Health Sciences University. This is a collaborative life science building, multi-scale microscopy core. It was a very noisy site. They were in a location that was right next to a river. They had streets, a bridge, river traffic. You can even see a streetcar in the photograph on the left, right in front of the building. So they were very concerned. The site failed to meet the specifications of the electron microscopes. So very challenging conditions and really unknown impact from future activity. They didn't know what the future held, but knew it could potentially get much worse with some construction plan nearby and additional streetcars and traffic. So during the first phase, they installed 4 transmission of these cryo TEM electron microscopes, 10 ultimately, and I think even a few more since. So it's one of the largest cryo electron microscope labs in the world, one of 3 centers for excellence in the United States by the NIH. So what they did, we would consider this the best case approach or the best practices approach. They decided to use an 18-inch tall raised access floor for flexibility, so they would have access to the underside of the instrument and access to the isolators if ever they needed that. And you can see the image on the right showing the inner isolated platform nested into the outer rigidly supported platform. Photograph on the left showing the taped over with vinyl the platforms before the tool has been installed. So what they're able to do is, with this clean approach, they were able to achieve the floor vibration criteria of the instruments And basically, they haven't been able to see any vibration artifact from any of the city activity, including the trains when they go right by. They see absolutely nothing. So it's been very successful. You can see in the curves again, the red curve is the floor and the blue curve is the isolated platform. And once you get above 30 hertz or so, you don't see any vibration isolation. Well, in fact, it is isolating. That's just evidence that at above 30 hertz or so, your isolated levels are really controlled by energy coupling in from acoustics and other structures, other paths, rather than vibration coming up through the floor. So just highlighting that the real critical vibration frequency range is about 0.5 hertz to 30 hertz. Above 30 hertz doesn't really matter. Below 0.5 hertz doesn't really matter either, because everything tends to be moving together as a rigid body. So the idea is, rather than ever quieter buildings, quiet islands rather than quiet buildings, or more modest plans for making quiet buildings and planning ahead, instead planning ahead on discrete, isolated, quiet islands in a few dozen places in the buildings. So the advantage: flexible design accommodates custom footprint requirements tailored to the tool. It's always compatible with the internal vibration isolation system in the tool when using the serial type with the stiff rubber mounts, and provides the highest possible levels of vibration attenuation down to below 1 hertz. So in summation, be conservative, plan for vibration levels to rise over time. The second is the isolation system always must complement, not fight the tool's internal vibration isolation system. So it's not necessarily the best vibration isolation system. It's the vibration isolation system that's the most compatible with the isolation system in the tool. And finally, to think in terms of quiet islands, not quiet buildings, for the reasons we've talked about. So that brings us to the end of the discussion. We've got a few minutes to discuss any details or any questions. So I think I'll turn it over to John again to moderate questions and answers.
Yeah, thanks, Steve. That was great. And again, yeah, a reminder to the attendees, if you have any questions, please type them into the section there on the right for questions. I do have a few here, which I'll start with. So the first one is, if I don't know the exact tool set that will be installed, is there a design protocol I should follow to allow future installation of quiet islands that may or may not require active isolation?
Yeah, well, that would be the third case study, what we talked about for Oregon Health Sciences University. What we'd consider best practices would be, designing around having a raised access floor, say 18 inches or 24 inches high over, a concrete subfloor, which should be, at least 8 to 12 inches thick, adequately supported. So, both actively isolated and rigid quiet islands could then be designed to match the tool footprint and the other requirements, and easily installed or moved around when needed. So I think, again, just in summation, best practice is a raised access floor, 18 or 24 inch over a thick concrete slab.
Okay. Next one, can these vibration attenuation techniques be used to compensate for general instruments over cantilevers or on higher levels in a building, or are these techniques mostly reserved for high precision instruments?
Yeah, these are strictly to isolate high precision instruments from low frequency, low amplitude building floor vibration. What we're not doing is, anything for a gross seismic event. This is not any sort of an earthquake mitigation structure. It's a whole different type of technology. Typically involves, bearings or things like that to allow the building to move a little bit. But if I understand the question, no, this is only for isolating ultrasensitive instruments from low frequency, low amplitude building floor vibration.
I think the question is maybe, okay, so I'm installing something, on an upper floor of a building, what can I do there about vibration isolation?
Well, everything applies that we talked about. So what you're going to see in a higher level building is you're going to see higher levels of vibration, and you're going to see it at lower frequencies, right? When you go up to extremely tall buildings, you're going to have the building sway be, a period of, good grief, I don't know, 10 seconds or maybe more. And that is such a low frequency that it's outside of the bandwidth of the active systems and really outside of the vibration criteria of the instrument. But you're not going to see ultra-sensitive instruments, installed in very, very high levels in floors. I think probably the highest we see would be something like 8th, 10th floor is about the highest I ever recall seeing something like an electron microscope.
Yeah. Okay. Another one, do the active isolators work for transient vibrations as well as steady state, or do they need time to sense and respond to the vibration?
Yeah, that's a good question. They work for both. It doesn't really matter. It can be a random event. It can be a discrete thing. It can be something that goes bump in the night. It doesn't really help even that it's periodic noise. So no, it works with random noise as well as it works with periodic noise.
Okay, thanks. Does an 18-inch raised access floor provide adequate clearance for most isolation pedestal systems?
I would say yes, that's probably the minimum. I would prefer 24-inch. I think it just gives a little more room down there. But I would say 18 probably would be able to handle any commercial system. Yeah.
Okay. Yeah, we have quite a few. What is the sensor used in the active isolator?
So a couple of ways to go about it, really two different technologies. You can either measure acceleration or measure velocity. So acceleration is measured with accelerometers. So like you'd have in a car an accelerometer to deploy an airbag, you can have extremely sensitive accelerometers to sense acceleration. But the other way is to measure velocity instead. Accelerometers use the piezoelectric effect, but velocity sensors use a magnet and a coil, and the magnet and coil moving with respect to each other gives a velocity, it gives a voltage proportional to velocity. So accelerometers give you a voltage proportional to acceleration. Velocity sensors or give you a voltage proportional to velocity. We use velocity sensors simply because they're more sensitive at the low frequencies. So an accelerometer is going to give you much better information at 100 hertz. But if you're measuring down to sub-hertz, it takes an extremely sophisticated accelerometer to measure anything at those very low frequencies, whereas velocity sensors pick that up much more easily. So just in summation, we use velocity sensors rather than accelerometers because they're more sensitive at the low frequencies. And if you can't measure it, you can't cancel it.
Yeah, okay. Another one, regarding vibration isolation on a slab.
Say one more thing. I kept saying velocity sensor. So a geophone type velocity sensor.
Okay.
Go ahead.
Regarding vibration isolation on a slab on grade, is there a point where the thickness, where the thickness of concrete no longer helps with the vibration isolation or actually hinders it?
I would say it never hinders it. I think the point of diminishing return would depend on, a number of things, the size of it, what's going on beneath there. So I don't want to say how thick it should be. I would say that it varies, but having it thicker doesn't hurt.
Okay. We have 1 minute left. I think this is going to be the last one, but again, if you have questions, please contact us. Let's try to get this one in. How do the active isolation systems compare to a plinth on pneumatic spring system in terms of both the space required and cost?
In terms of the space required, the plinths tend to be not customized to the tool footprint. Plinths tend to be kind of more of a brute force approach. There's it's going to be larger than the footprint of the tool. They tend to be quite massive and go down a bit just because of the length to thickness ratio you want to have for concrete is going to lead to a very large block. So the active systems are smaller because they are typically tailored to the footprint of the tool. They're no larger than they need to be. They're more easily manufactured to a custom requirement than pouring a large block. In terms of cost, the active systems would be more than a plinth, but it really depends. It's hard to compare apples to apples. You know, if it was a very large plinth with a number of air isolators under it, compared to a small active system, because it didn't need to be very large, you know, the prices might be you know, much more comparable. So typically the active systems, you know, are going to be more than a plinth. It's hard to give an exact number of how much, but you know, you definitely expect the active system to be more expensive than a plinth on air.
Yeah. Okay. Well, that brings us, you know, to 2 o'clock. There's still some questions. I'd encourage you to contact Steve at steve.ryan at ametek.com. But thank you for attending, everyone.
Thank you.